Let's continue talking about hybrid orbitals by considering mixtures of more than just one s and one p orbital. So let's look at sp2 hybrid orbitals. That's how you say this, sp2. And we're going to look at a trigonal planar molecule, borane, BH3, and we're going to figure out how we can mix orbitals and describe how it ends up being trigonal planar. So if we look at the boron electron configuration in the ground state, it's 1s2, 2s2, 2p1. Again, this is what we learned back in chapter 6. But in order to form 3 bonds, we've got to somehow get 3 unpaired electrons. And what we're going to do is add energy to this system to promote one of those 2s2 electrons up to the 2p subshell. So now all 3 of those electrons are unpaired and pointing in the same direction. Now we can combine them with electrons on other atoms and form bonds. But before we do that, we want to make sure that they're all equivalent bonds, because at the moment, an s orbital would be very different than a p orbital in overlap. So to maximize the overlap, we mix that 1s with the 2 occupied p orbitals to form sp2 hybrid orbitals in the n equals 2 shell. There's 3 electrons in those hybrid orbitals, and I'm just showing that there's one leftover pz orbital containing no electrons that has not been mixed, just to emphasize that we still have that remaining orbital. Geometrically, if we look at the shapes here, we see that the 1s orbital can be combined with 2 different p orbitals. The mathematical combination here is a little bit trickier, but you can actually write equations to generate these mixed orbitals that point towards the corners of an equilateral triangle. And if you show just the large lobes, that's what does the overlap with hydrogen. You see why it is that we get a trigonal planar structure from sp2 hybrid orbitals. Similarly, if we mix 3 p orbitals with an s, we get sp3 hybrid orbitals, as is the case in methane. Once again, we're going to consider only the valence electrons on carbon. Forget about the core electrons, they don't play a role. And if I look at orbital diagrams, the ground state orbital diagram looks like this for carbon. Here we have 4 electrons, but only 2 of them are unpaired. So we go through a promotion step to kick one of these original s electrons up into the p. This is a higher energy arrangement than this is. And then in order to make 4 equivalent bonds, we have to mix all 4 of these together to form the 2 sp3 hybrid orbitals. And once again, we can show this geometrically. It's a little bit tricky to see how the mathematical combination is, but these are the original orbitals. When we mix them together, hybridize, we get these 4 sp3 hybrid orbitals, whose large lobes point towards the corners of a regular tetrahedron, and that's why we get the tetrahedral shape in methane. Now we're in a position to answer my original question from the previous talk: why isn't the bond angle in water 90 degrees? So applying this to water, we see that the water structure has to use sp3 hybrid orbitals. The reason we know this is because its electronic geometry is tetrahedral. And once you see that the electronic geometry is tetrahedral, that can only be due to sp3 hybrid orbitals. 2 of the orbitals are used to form overlap with the hydrogen 1s orbitals and form the bonds. And the other 2 hybrid orbitals are used to hold the non-bonding pairs. And that's how it is that we get the bond angle that we see in water. Finally, the book does talk about hypervalent orbitals, which means orbitals or structures going beyond the octet rule. And modern calculations do show that the d orbitals don't play a very prominent role in forming these sorts of structures. Nonetheless, for decades, it was believed that the d orbitals are also involved in hybrid orbitals. And because of that, If you do reading outside of class, you are likely to encounter the hybrid orbitals involved in trigonal bipyramidal structures as well as octahedral structures. So I want you to at least know these rules. Trigonal bipyramidal electronic geometry is considered to be formed from sp3d hybrid orbitals. Octahedral geometry is formed from mixing two d orbitals with the sp3. And here's a sort of a graphical way of seeing this. This column mixes an s, 3 p's, and the 3dz squared orbital, which looks like this, to give us the sp3d hybrid orbitals. It describes the shape perfectly. Even if the d orbitals are energetically not particularly involved, this combination does describe the shape perfectly. And for sp3d2 hybrids, the octahedral shape, we mix two d orbitals, the one pointing directly up and down, and the d x squared minus y squared, which points directly along the x and y axes. And once again, that gives us a good heuristic description of how it is we end up with the shape in octahedral orbitals.